Hypothesis is simply a claim that you want to test. You can think of it as your initial belief or assumption that can be checked with data. To understand this, let's consider some examples. Suppose a company claims that a new scooter model gives an average of 50 km per liter of fuel. We are making a claim about scooter's performance. Here, hypothesis could be average mileage of scooter is 50 kilometers per liter, and to test it, we could take a sample of scooters, measure their mileage, and see if the data supports the claim or not. Or we might claim that proportion of unemployed people in two states is the same. Again, we can collect the data from both the states and test if that is true. So, whenever you see the word hypothesis, you can think of it as a testable statement, something that you can support or reject with the evidence. Let's move on to hypothesis testing. It is a method that helps us to decide whether the claim that we made is credible or not. We can think of it like a courtroom. If someone is accused of a crime in court, we do not immediately say that he is guilty. We start by assuming that he is innocent, and that's our default claim. And only if the evidence is strong enough, we say that the person is guilty. That is what exactly happens in hypothesis testing. The starting point is accused person is innocent, and this is the null hypothesis. Challenger or exact opposite of this statement is accused person is guilty. And this is known as alternative hypothesis. If the evidence is strong enough, we reject the assumption and find the accused person guilty. Every test has two competing statements, the null hypothesis and the alternative hypothesis. Null hypothesis is denoted by H naught and it is the established or existing belief. This is generally accepted or assumed to be true, and it assumes that there is no effect, no difference, or no change. Alternative hypothesis uh, is denoted by H1. It is also called as challengers or research claim. It is what we want to test or prove, and it challenges the existing belief. It supports that there is a effect, change, or a difference. So, if a statement sounds like is equal to or is equal to some value, no difference, same, no effect, then you can put it into the null hypothesis. And if the claim sounds like there is an effect, there is a difference, or there is an improvement, then put that into alternative hypothesis. Whenever we make a decision from data, there are two mistakes we might make, type 1 error and type 2 error. Type 1 error happens when null hypothesis is actually true, but we wrongly reject it. And it is also called as false positive or a false alarm. Type 2 error happens when null hypothesis is false, but we fail to reject it. And it is also called as false negative or missing effect. Type 1 error is a alarm without fire, and type 2 error is no alarm during fire. Suppose a person does not have COVID 19, but the test says he has. Then there is a false positive. That is, test result is positive falsely. So, because of this false positive, the person who is tested positive might have to isolate, unnecessarily get worried, and miss the work or school. But in reality, he is healthy. In contrast, suppose if a person has COVID 19, but the test says he does not, then this is a false negative, like a missing fire alarm. And he continues moving around, meeting others, unknowingly spreading the virus. And because he thinks he is healthy, he may delay the treatment, get much sicker, and in severe cases, even risk his life. So in most of the cases, type 2 is more dangerous. Let's consider some examples to understand how type 2 error is more dangerous generally. In case of a medical test of a deadly disease, type 2 error is more dangerous. In a court trial, type 1 error is more risky because convicting an innocent person is unfair. At airport, during security checking, making type 2 error is risky. That is, if a danger during security checking, if we miss a dangerous passenger is risky. In a factory, in case of quality control, letting defective product reach the customer is risky. So here type 2 is more dangerous. Here type 2 error is more dangerous. Probability of type 1 error is alpha or level of significance, and we choose it before testing. Common choices for alpha are 0.05 or 0.01. When the cost of type 1 error is very high, in the situations where we cannot afford to fail, we use alpha at 0.01. This involves the situations like safety testing of aircraft parts, clinical trials for a new medicine, or a medical surgery. Here we use alpha at 0.01. While in business situations like comparing sales before and after marketing campaign, we use alpha as 0.05. As a cost of missing a real effect is very high. In such cases, we prioritize a lower risk of type 2 error to ensure we detect any meaningful improvement. This testing, if you decrease one type of error, other tend to increase. Lower alpha means favor false positives, more false negatives, and the higher alpha means more false positives and favor false negatives. Now that we have understood the null and alternative hypothesis, the next step is to see what kind of test we should use. And here is the key. It is the alternative hypothesis that decides whether to go for one tail test or a two tail test. Let's start with one tail test. This is when we are only interested in change in one direction, either greater than or less than, but not both. Alpha sits in one tail of the curve. So there is just one critical value. If we are testing if the average weight of apples is more than 100 grams or if failure rate is less than 5%. Imagine a bell curve where only one end is shaded, that is the rejection area. Two tail test. Let us look at two tail test. Here we are checking for change in either direction. It could be greater or it could be less. In the two tail test, alpha gets split into two equal parts, one on left, another on right. This gives two critical values. For example, testing if mean weight of apples is not equal to 100 grams. Okay, I will tell you a quick way to decide if your test is one-tailed or two-tailed. If H1 says greater than or less than, it is one-tailed. If H1 says not equal to or different from, it is two-tailed. This bell-shaped curve is a probability distribution, and the grid shaded region in the middle is a confidence level. It is where most of our sample results will fall if null hypothesis is true. It is denoted by 1 minus alpha. In this case, it is 95%. You can think of it as a safe zone where we expect our shots to land most of the times. Now look at these two small red tails on either side. Each tail is labeled as alpha by 2, that is 2.5%, and these two combined is 5% in total. If the test statistic fell in these regions, it is rare and so we reject it not. Let's see what is critical value. It is the value of test statistics which separates critical region and acceptance region. It depends on first, value of alpha, and second, if the alternative hypothesis is two-tailed or one-tailed. Critical region. This is like a danger zone. If your test statistics lands in this region, you reject it not. There are two types of decision rules. One is using critical value and another is using p-value. Let's see the critical value approach. First of all, decide your risk level alpha. From alpha, check the tables and get your critical value. This critical value defines the boundaries, critical region and acceptance region. Now comes your test statistic. This is the actual result you got from sample. If test statistics fall into rejection region, that is, if calculated Z is greater than tabulated Z, then reject H naught. If the test statistics fall inside the acceptance region, that is, if calculated Z is less than tabulated Z, then accept H naught. Or we fail to reject H naught. Here I have taken Z as a test statistics for our understanding only. The statistic will depend on whether you are using Z test, chi-square test, t-test, and so on. P-value. Let's see what the p-value is. P-value tells us how surprising our data is if the null hypothesis is true. We use this number to decide whether to stick to our current belief, that is the null hypothesis, or to switch to the challenger's belief, that is alternative hypothesis. So the p-value helps us make an evidence-based decisions rather than just guessing it. If the p-value is very small and if the null hypothesis is already true, then it is very unlikely to get the data that we are getting, which hints null hypothesis might not be correct. And if the p-value is large, then data is compatible with the null hypothesis and we do not have enough evidence to reject it. Once we have a p-value, then we compare it to the significance level alpha, which is typically 0.05, and this gives us a clear rule. If a low p-value below alpha, that is if alpha is less than 0.05, means observed result is very unlikely under H0, and that's why we reject H0. A high p-value that is above alpha means our observed result is consistent with H0 and we fail to reject H0 because we do not have a strong evidence against it. Suppose our null hypothesis is that new drug has no effect and it is same as placebo, and our alternative hypothesis is drug has significant effect. Then we run a study, collect the data and calculate the p-value. And suppose our p-value comes around 0.03 and which is less than our threshold value alpha, which we generally use as 0.05. So our data would be quite unusual if the null hypothesis is true. So we have enough evidence to reject the null and conclude that the drug has a significant effect. Imagine you think coin you have is fair and you flip it 10 times, but you get heads 9 times. This is showing that the coin we have is not fair. It was easy in this case to identify that the coin is not fair because we got 9 heads. But what if we get 4 or 6 heads out of 10 flips? In such scenarios, p-value comes handy and it helps us to decide firmly whether to reject or accept H0 rather than just guessing it. To wrap it up, hypothesis testing follows 5 clear steps. First, state your null and alternative hypothesis, then set your alpha, collect data, and calculate test statistic. find the p-value, and finally make your decision. So that's the complete cycle.